Today I'm going to talk about the development of nanostructured heterogeneous catalyst for these metal CO2 batteries. So let me introduce these metal CO2 batteries. And before that, what is the problem definition why we are looking for these metal CO2 battery or new chemistry? I know these days we talk mostly about the CO2 emissions, greenhouse effects, climate change related to that. And of course, there are a lot of efforts going on converting CO2 into useful products. But we also know that these are very energy intensive processes. And at the same time, of course, with the new catalyst development, we are looking into the more less energy intensive processes. But at the same time, this is one approach where we can directly convert the CO2 into the energy source. So this is one way to look into it as far as Earth atmosphere is concerned, that how to mitigate the CO2 emissions. At the same time, when we look for the Martian atmosphere, if you see the Martian atmosphere, it is 95% CO2. So now what if we can develop this metal CO2 battery and use it in the Martian atmosphere? And of course, this is one of the major aim for this development of metal CO2 battery for the interplanetary Mars missions. So when we go for the interplanetary Mars missions, we have to use the energy storage system for landers and rovers for their longevity of the missions. Now, as of now, they all use primarily the lithium-ion storage battery system, which is having limited capacity, limited life. So the longevity of the mission is also affected by the limitation of the energy storage devices being used. At the same time, there is an associated cost in terms of mass and volume of these payloads when we send these missions from Earth, because you need to carry an extra weight of these energy storage devices. So the idea is, what if we use the local atmosphere to generate that energy required to power these landers and rovers on the Martian atmosphere? So this particular development of metal CO2 battery is basically targeting two sites. One is the Earth atmosphere, taking care of the CO2 emissions, at the same time developing it for the Martian atmosphere for the interplanetary Mars missions. Now, when we look into the lithium-ion battery and other energy storage technologies, so we should have certain A's, technical A's in terms of using this new chemistry. And that is where this comparison is. So lithium-ion battery, we mostly know that this was developed late in 70s and commercialized first time in 1991 by Sony. And of course, 2019, this discovery of lithium-ion battery got the Nobel Prize as well. But the limitation of this lithium-ion battery is it is having a limited capacity, like 250 watt-hour per kg. That is the theoretical energy density. At the same time, now if you compare with the metal CO2 battery, lithium CO2 battery, for example, which was first time introduced in 2014, it has a theoretical energy density of 1876, which is 7 to 8 times higher than the currently used lithium-ion batteries. So of course, there is a clear advantage, technically advantage, in going for this kind of new battery technology. While we talk about the lithium-based resources, we know there is a limitation of lithium-based resources. So people are now looking for the alternate metal chemistry. That's where the sodium ion coming into picture. And that's where if you compare even the sodium CO2 or potassium CO2 batteries, even if you go for the sodium or potassium CO2 batteries, their theoretical density also is much higher than the currently lithium-ion batteries. So obviously there is a obvious interest in developing this technology for the future. So sodium CO2 battery, it was first time introduced as a concept in 2016, and potassium CO2 first paper was in 2020 in the literature. Now, when we see the development of this metal CO2 battery, as I mentioned, in 2014, this was first conceptualized. Before that, in 2013, this first time it was introduced as a primary battery. Primary battery means not rechargeable, not secondary. Only one time it can be charged and then it can be used for that. So that was in 2013. That's where the first report came on the lithium CO2 battery. And next year itself, the first secondary battery was introduced, in which there were some few cycles of charge and discharge were demonstrated. And since then, there has been continuous development in this area. From 2015, then 16 sodium battery came. Then people started using different kinds of catalysts for increasing the reversibility of this battery, because that was a challenge. And so this paper is from Chemical Reviews, and this is where we started contributing from our group, lithium CO2 battery suitable for Mars exploration. So in 2021, we first time demonstrated the lithium CO2 battery for the Martian atmosphere. And we conceptualized it that it can be used for the Martian atmosphere as well. And of course, after that, there has been a lot of development in terms of different strategies which are used to increase the performance of this lithium CO2 battery. So just to introduce this lithium CO2 battery chemistry, so basically it involves the electrochemical reduction of CO2. It's a redox reaction which is involved, and there is an anode which is like metal-based anode, lithium, sodium, potassium, and here there is a cathode from where you introduce the CO2 in the system. Because CO2 is a gaseous phase, you have to continuously supply the CO2 from one side. So unlike the typical energy storage devices, it's not a closed system, it's an open system where CO2 is continuously pumped towards the cathode. So CO2 is coming towards the cathode, and lithium ion goes to this separator, reacts with the CO2, and that's what it follows this reaction on the cathode. These lithium ions react with the CO2 and forms lithium carbonate plus carbon. So it's basically a combination of metal anode and electrochemically reduced CO2 which generates the energy in this process. Now in this process, if you see that discharge is lithium ion react with the CO2, it forms metal carbonate or lithium carbonate. The issue with the lithium carbonate is the reversibility, and that's how first time when it was introduced as a primary battery. We will come to it a little later. So as I said, it is having a continuous CO2 system. So it is assembled like this, where you supply the CO2 continuously in this closed chamber, and reaction happens on the cathode side. So this is how typically it looks. This is your metal anode. Then there is electrolyte. Then there is a catalyst. I will come to that. What is the role of the catalyst here? And this is your porous cathode through which you pass the CO2. And that's where the reaction happens. This is the primary reaction, which is right now established as per the known mechanism. So lithium reacts with the CO2 and forms the metal carbonate and carbon, which is a solid product. And that is where, again, you need to have the porous cathode to accommodate that solid active sites, other than providing the passes to the CO2 in this battery system. So this is basically the CO2 fixation in terms of CO2 emissions on the Earth. It goes like CO2 electrochemical reduction. It forms Li2CO3 and carbon. When it comes to the Martian atmosphere, it is more like utilization of the CO2 atmosphere, and that is where the metal carbonate reacts with the carbon. It forms again lithium and CO2, and this is how the total reaction pathway is going around. So now with this, what are the challenges involved in the system? So let's talk about that. So as I mentioned, lithium forms the lithium carbonate and carbon, and this lithium carbonate, basically it is getting deposited on the surface of the cathode, on the cathode. And this solid product of lithium carbonate and carbon that deposits, and that basically hinders the further possible active sites for the further reaction. So not only it hinders the path, but there is another challenge that this lithium carbonate is basically a very thermodynamically stable compound. It does not dissociate so easily in the reversible way. So that's where we need the efficient catalyst so that we can push the reversible reaction, so that we can have the reversibility of this system. So now the higher energy required for the decomposition. If we go for the higher voltage, which is required for its decomposition, it doesn't happen automatically. So when you apply the high voltage, there are chances of electrolyte degradation. So that's another problem. Of course, you can go into the reversible side by increasing the voltage window, but then you are compromising with the electrolyte stability. That's another reason the performance comes down. So there are multiple challenges here involved. And of course, the insufficient decomposition of discharge products, that basically loss of reaction sites, reduce the conductivity, and ultimately it goes to the premature failure of the whole full cell. So with these challenges, the practical issues what we face is lower practical energy density. Of course, the theoretical energy density might be very high as compared to lithium ion, but when we go for the practical cell, because of these reasons, the actual energy density is very low. A small cycling life, in fact, only few cycles were demonstrated in the beginning, and then high energy intake for charging. So in that way, it is not energy efficient process, because the discharge voltage which is generated and the charge voltage, it is higher than that. So it is not energy efficient process in this way. So now how we try to overcome these challenges in our group. So we have multiple approaches in our group to handle these situations. So first is to develop some catalyst so that we can increase or improve the reversibility of the system by bringing down the activation energy and by providing more enabling path for the reversibility of the reaction. Second, the cathode structure itself, because cathode structure has to be accommodated enough, it has to be porous enough so that not only just it passes, it allows the CO2 gas passes, but also it allows the accommodation of these active sites like by solid products, metal carbonate and carbon, at least for time being till it decomposes. Third is the electrolyte optimization, not only for accommodating the high voltage which is required for the dissociation, but also at the same time, when we are looking for development of these batteries for the Martian atmosphere, it's not just the gaseous atmosphere which is changing, but also the temperature and pressure conditions are way different than the Earth atmosphere. So Martian atmosphere, temperature varies from -50 to +40, +50 degrees Celsius. So you should have an electrolyte which can withstand these temperature range. Then exploring the different metal anodes, that's another approach in our group, because lithium is not very resourceful for a continent like India. So we are looking for potassium or sodium source as a metal. And of course, we are also looking what are the theoretical exploration of these reaction pathways, because not many studies are done to look into the in situ reactions, what is happening inside. Right now, it is understood that metal reacts with the CO2, it forms metal carbonate plus carbon. But at different conditions, how these reactions are changing, that is still yet to be explored. So today, I will be focusing more on this catalyst part, considering the audience and the theme of the symposium. So we developed different kinds of catalysts. One is the ruthenium nickel bimetallic catalyst, and for the better support, we have dispersed it into the multi-wall carbon nanotubes, which is generally used as a good support. And then in our group, we have been working on candle soot in different ways. So we will compare the performance of candle soot as a catalyst, pure candle soot and compare it to the multi-volt CNT. And we will demonstrate that candle soot works better than the multi-volt CNT. And that's why we will now switch from ruthenium nickel to multi-volt CNT to ruthenium nickel candle soot nanoalloy catalyst. So first, ruthenium nickel multi-volt CNT bimetallic catalyst. This work was published in Camps of Scam last year. So now, why ruthenium? Of course, ruthenium is a transition metal. We all know it has been used in the catalysis. So, and especially in the metal CO2 battery or metal O2 battery, this promotes the easier formation and decomposition of this discharge product, lithium bicarbonate, Li2CO3. And on top of that, if you have nickel nanoparticles, which improve the reversibility further for this reaction. So now we are alloying this ruthenium with other metal to enhance the electrocatalytic activity through the ligand geometric and electronic effects. And we are anchoring finally this ruthenium nickel alloy on the multi-volt CNT for a better dispersion to provide the improved electron transfer. So that is the goal for this particular synthesis of ruthenium nickel on multi-volt CNT. This is the synthesis. So we have taken the nickel salt and ruthenium chloride and multi-volt CNT, did the hydrothermal process under certain conditions and pyrolysis at 350 degrees Celsius. This is how we decorate the ruthenium nickel nanoalloy bimetallic catalyst on these multi-volt CNTs, and then use it as a support, as a catalyst, cathode catalyst support to use on the carbon cloth, which is used as a cathode. These are just typical characterization techniques to ensure that we have the ruthenium nickel multi-volt CNTs by XRD and the TEM and HRTM. So you can see how the ruthenium nickel bimetallic catalyst is nicely dispersed on the multi-volt CNT. And this is what we see the performance of this ruthenium nickel multi-volt CNT catalyst supported metal CO2 battery system. So this side we have tested the battery in the pure CO2 atmosphere, while this side we have tested the battery in the CO2 Martian atmosphere. So we have used the simulated Martian atmosphere where it's exactly the same gas composition, like 95.2% CO2 plus some 2% CO and some other gases. So we have used the simulated Martian atmosphere. And what we see here is from this cyclability that as compared to the multi-volt CNT, which is like black dotted curves, the ruthenium multi-volt CNT and ruthenium nickel multi-volt CNT, the over potential between the charge and discharge is minimized when we use the ruthenium nickel multi-walled CNT. And also, if you see in terms of capacity with respect to the different current density, so we are using first cycle to 80th cycle, and we see, of course, with cycling the overpotential increases, but the system is stable up to 80 cycles. While when we go for the Martian atmosphere, the performance improves further, and there is a reason because some additional gases which are coming in the simulated Martian atmosphere, they rather help the system. So presence of minor amount of CO that helps into the reversibility. So CO2 Mars, we can see this is further minimized, and of course ruthenium nickel system is working better than the only ruthenium system. Here we are able to achieve up to 93 cycles. So what we see, there is a reduced overpotential and increased the cycle life while introducing the Martian atmosphere as compared to the pure CO2. What we also see is that even within the CO2 or within CO2 system, the overpotential is less when we talk about the ruthenium nickel multi-walled CNT system. So high cycling life at till 180 cycles with the current density of 200 milliampere per gram. And we were able to use the system at different current densities, which is important for the different applications. And then, of course, there is an enhancement in the cycling life and reduced overpotential. And this developed catalyst also shows that it can be used in the variety of atmospheric conditions. With this, we move to the use of candle soot, introducing the candle soot rather than multi-walled CNTs. And that is the specialty of our group, to use this material as a catalyst. So this work was again published last year in ACS Applied Energy Materials, where we have compared the performance of candle soot nanoparticles over multi-walled CNTs. Now, why candle soot is important and why we are looking for? So, of course, this is one of the most facile way to synthesize the carbon nanoparticles ever reported in the literature. You just lit the candle and collect the soot. That is how you get the candle soot nanocarbon. The interconnected network of these carbon nanoparticles that basically facilitates the transfer of electrons, which is good for the energy storage devices or even on the catalytic side. High surface area that again provides a large number of active sites, which is again essential condition for any catalyst, and of course lower cost compared to any conventional catalyst synthesis method. So what happens? What is this candle soot? As I said, you just have the candle, burn it, and collect the soot, and then that's how you deposit the candle soot on any substrate. When we look into this candle soot in the microscopy, FESEM or TEM, what we see, they're having the fine interconnected network of carbon nanoparticles, which are around 40 to 50 nanometer in size. Of course, it depends on where do you collect the soot, whether you're collecting from the tip of the flame or middle of the flame. It depends. It gives the different kinds of soot particles, because when middle of the flame, there is an incomplete incombustion of wax, and there are a lot of impurities present in that, and that becomes non-conducting. When we look this material, typically ID by IG ratio is 1.12, which means it's an amorphous carbon, and the surface area of as collected soot is around 100 meters square per gram, which is not very great, but we can enhance it by different ways. So as I was mentioning, same soot, you can have amorphous feature as you collect it, but by different ways. You can have graphitic features, you can have nanodiamond features, and fluorine feature also embedded in the same material. It depends on flame temperature, flame height, what is the wax composition, how long you are depositing, and the wick dimensions. So these are the very simple parameters you can vary to find the variation in your material depending on your final interest. So here we have collected the candle soot like this, and did the annealing. This annealing is done further to ensure that there is no impurity remaining. And this annealing also increased the surface area a little bit from 100 to, let's say, 150 meters per gram. And then we did the ultrasonication in isopropanol PBDF, made the solution of it, and deposited it in the carbon cloth, which is used as a substrate, catalyst support. And this candle soot was used as a simple catalyst. Similarly, for comparison, we have used the multi-walled CNTs. Again, prepare the solution of multi-walled CNTs. Similarly, we have put the solution of multi-walled CNT in the carbon cloth, used it as a electrode, cathode. So, and then again, we have used it for the Martian gas as a system. And so this is typical how this looks like. This is candle soot, this is multi-walled CNT. We can see the surface area is around 90. Here it is 600. Multi-walled CNT is around 90, while candle soot is increased to 600 by activation. And again, the candle soot, it was originally 1.12, which is now reduced to 1.03. It's like a quite amorphous region, unlike the multi-walled CNTs. This is what you see in terms of performance of candle soot and multi-walled CNTs at different current density. So in all the cases, in all the different current density, what we see is the overpotential for the candle soot is less than the overpotential for the multi-walled CNT, which means it is working more efficiently than the candle soot. Not only that, in terms of total number of cycles which we can achieve, at any current density which we can see, let's say for 50 milliampere per gram, candle soot was having higher cyclability, 35 as compared to 28, and at 200 milliampere per gram we were able to achieve 84 as compared to 68 for the multi-walled CNT. Even at given current density, you can see it goes up to 84 cycles, and this multi-walled CNT fails at lower number of cycles. So what we have tried to establish is that rather than going for the multi-walled carbon nanotube as a support for the catalyst, we can still use the candle soot more efficiently. And this basically leads to the next problem definition, that now the ruthenium nickel, which we have established as a better system, can be now integrate this ruthenium nickel, which is CO2 reduction catalyst, with the candle soot to further improve the battery performance. And that is what we have done in the next work. Now the ruthenium nickel and candle soot nano alloy catalyst. This again was published last year in batteries and supercapacitors. And so here again, it's a very simple synthesis process, just like what we have done. And we have taken the ruthenium chloride and nickel nitrate salt, and then did the hydrothermal process in the presence of candle soot carbon. Now we have the ruthenium nickel deposited on the candle soot carbon. And this is what we see in the TEM pictures, that these are the ruthenium nickel catalyst, which is having now the candle soot particles very nicely dispersed uniformly on these structure. So basically the interconnected network of the candle soot nanoparticles with the high surface area, that is providing the more enhanced electron transfer to the external circuit, and that also provides a large number of reactive sites available for the reaction, for the CO2 redox reaction. And this is how the electrochemical performance goes. So we can see the ruthenium nickel candle soot carbon, it gives much higher current response as compared to two other systems, only candle soot and ruthenium candle soot. And with respect to the different systems, like this is at different current density, we see the overpotential value and also full discharge value. So when we fully discharge, want to use it as a primary battery, we can really go up to nearly 15,800 milliampere per gram, which is way higher than reported values in the literature. Similarly for different cycles. So here, first time we were able to cross the 100 cycles of charge and discharge with the help of this ruthenium nickel on the candle soot carbon. Even for the higher current density, like 200 milliampere per gram, this is a comparison between the ruthenium candle soot, ruthenium nickel candle soot, and we can see as compared to 72 cycles with respect to the ruthenium candle soot, ruthenium nickel candle soot gives you more than 100 cycles of charge and discharge. So other than this, we are also looking into the development of electrolytes, as I mentioned, because when we are looking for the lower temperature region, the same electrolyte will not be able to work. So we are looking onto the binary solvent mixture to enhance this operational temperature range for these metal CO2 batteries from -20 to +40. That is our primary goal, first goal. And in this range, we are looking for improved CO2 solubility, so that there is an enhanced interaction between the lithium ion and the CO2 molecules. So for that, we are looking for bisolvent system, where one solvent is having good conductivity and the CO2 solubility. At the same time, solvent V is having a desirable freezing point. That's where we can approach for the lower temperature application of this metal CO2 battery. We are also looking into the different liquid electrolyte challenges, because ultimately when we want to go for the safer batteries, solid electrolyte is the way forward. So parasitic reactions of solvent with both lithium and CO2, this is one of the reason we want to switch towards the solid electrolytes. Flammability, volatility of the liquid electrolytes, leakage, and it's more because it's a semi-open system, unlike the closed system of other batteries like metal ion or metal sulfur. It's a semi-open system. One side it is porous, so we have to really look into the solid electrolytes to avoid the leakage, and limited cycle stability. That's again where we are another area. Of course, we have achieved till now around 200 cycles latest work, but if we compare it with the commercial batteries, lithium-ion batteries, that is where like we need to go towards minimum 1,000 cycles. So there is a long way to go. So the way forward for us, so we are looking into the different components. Today I just presented the cathode part. So cathode is structure and catalyst to further improve the cycling life. Electrolyte from liquid to semi-solid and semi-liquid or solid. Then again from lithium-based anode to other economical and abundant like sodium, potassium, magnesium and multivalent electrodes. And also we are looking into the low temperature region. And not only that, we are also interested to look into the pressure, because at Martian condition, the pressure is 0.01 to 0.1 bar. So again, the chemistry which we are trying to establish in the Earth atmosphere may not be valid. The same reaction pathways may not happen when we go for the reduced temperature region. Thank you for your kind attention.
Long live India and France friendship.